In this video, we will consider two examples of solids of revolution. The first is we have the region bounded by y equals 1 over x and the x-axis from 1 to 2, and we want to revolve it about y equals 2. So I already had the graph of y equals 1 over x done. This is the region we wish to revolve about the line y equals 2. So what we need to do is we take a generic x, make a segment, and revolve that segment about the line y equals 2. Okay, so what we're going to do is we're going to replicate the endpoints of the segment on the other side. So this point here reflects to that point, and this point here reflects to this point. All right, so let me clean this up. So I have this point and this point, so I get no. This point here is 1 plus a little bit. That's about 2 units out. So about there. So that's the inner circle, and this is the outer circle of our washer. Okay, so this is the washer. We like to find the area of this washer and then integrate. So we're gonna need the big radius and the little radius. The big radius is the distance from that point to that, which is the same thing as this distance. That's actually kind of easy to see. The big radius is 2 units. The little radius is the distance from here to this point. Okay, how do we find that? Well, one thing we know is from this point to this point, meaning this segment, has a distance of 1 over x. You need to remember, from the x-axis, always, if you have your x-axis and you have the graph, the distance from the x-axis up to the end of the graph, up to the point of the graph, is absolute value of f of x. So if f of x is positive, simply f of x. In this case, it's 1 over x. So this distance being 1 over x, we're looking for this distance. And we know that this whole thing is 2 units. So it's going to be 2 minus 1 over x. That's the smaller radius, the radius of the inner circle. Okay, so this distance here is 2 minus 1 over x. So then the volume becomes pi, the integral from 1 to 2. It's because x could be anywhere from 1 to 2. Let me change my pencil. So x can be anywhere from 1 to 2, because we're swiping from left to right, from 1 to 2, of big R squared minus little r squared dx. In this case, pi, integral from 1 to 2 of 2 squared minus 2 minus 1 over x quantity squared dx. Okay, see if I can FOIL this. Pi from 1 to 2, 4 minus 4 minus 4 over x plus 1 over x squared is how that FOILs out. So that gives you the pi, the integral from 1 to 2 of, distribute the minus and the 4's cancel out, you get 4 over x minus 1 over x squared dx. This is pi times 4 natural log of x minus plus 1 over x from 1 to 2. Put 2 in, 4 pi natural log of 2 plus 1/2 minus I'll put the pi outside. I'll put the pi outside. Minus, put 1 in, gives you 4 natural log of 1, which is 0, plus 1 over 1. So that's a 0. I have a half minus 1 gives us minus a half. So all in all, I get pi 4 times natural log of 2 minus 1 half. And that's our final answer. The next example is we have the region bounded by y equals 1/2 x and the x-axis from 0 to 4. Let's focus on that first. Y equals 1 over x from 0 to 4. Here's your 0, here's your 4, and 1/2 of 4 is 2. It's a linear function, y equals 1/2 x. Okay? So the graph looks like y equals 1/2 x. Okay. From 0 to 4. So this is your region bounded by the x-axis. This is the region. And we're revolving it now. We're going to focus on the axis of revolution. Revolving it about the y-axis. Where is the y-axis? The y-axis is here. We're revolving it about this y-axis. So this guy we're spinning it about the y-axis. Okay? So what we're going to get is something that kind of looks like a nice big cylinder where a cone is taken out from the center. The cylinder is a big cylinder, radius 4, but then we have a cone that's taken out. Okay, so in this case, since if we do cross section at x, we're gonna get some weird picture, some weird object. So we're gonna take the cross section at y, and we're gonna do the integral with respect to y, because then we will get our washer in this direction. Okay, so we have to rewrite our equations in terms of y. So I have y equals 1/2 x. You rewrite it as x equals 2y. Okay, and we don't have any more equations, so it's just simply x equals 4. This is x equals 4. So our region kind of looks like this. Let me put the region here. Our region looks like one, two, three, four. So this triangle revolves about this axis. So take a generic y, and you're looking at this segment and revolving that segment. So let's revolve that segment right about here to here. That's my big circle, and this is my inner circle. Alright, so I'm going to need big radius and little radius in terms of y this time, because we're integrating with respect to y, because we picked a y, we're looking at y. So the y maximum here is 2, y minimum here is 0, so we're going to integrate from 0 to 2. Okay, so the big radius is obviously 4 units. Wherever y is, the big radius is 4, whereas the little radius is from the x-axis to this point. And I think I mentioned this in class. I'm going to say that again here. So if you have a function given as x equals f of y, and you pick a point y on the y-axis, the distance from the y-axis to the point on the graph is f of y. technically absolute value of f of y, but if f of y is on the right side of the x-axis, it's simply f of y. So in this case, the distance from this point to this point, let me change my marker. So the distance from this point to this point is, this graph is y, x equals 2y. So that distance is just 2y. So now the volume is pi integral from 0 to 2 on the y-axis with respect to y of big R squared minus little r squared with respect to y. So that is pi integral from 0 to 2 of 4 squared minus 2y quantity squared dy. This is the pi integral from 0 to 2 of 16 minus 4y squared dy. This one is very easy to integrate. This is pi 16y minus 4y cubed over 3. Evaluate that from 0 to 2. So put 2 in, and then put 0 in. When you put 2 in, you get 32 minus 32 thirds minus 0. So that gives us 32 64 thirds pi. That's what I think I get. I may have made a mistake in the calculation here. I'll send you the correction on the email, but I think this is the correct answer. All right.